Today we're going to learn about everything you need to know about triangle segments and centers. We're going to start off with mid-segments. The definition of a mid-segment is a segment that connects two midpoints of a triangle. So right now I'm going to construct the midpoints and then construct the segments between them. So a couple of things about the mid-segments. If I take this particular mid-segment, you can see that I'm going to copy it. There's the length that I can see that it's the same length as that one and that one together. So altogether, the distance of this one, let me get rid of that. Another way to look at it is if I measure this segment right here, the length of it, I can see that it's 7.56. The length of this one is 15.11. If I calculate the ratio of the two, this one divided by that one, I can see that the ratio is 2. And this will be true no matter how I move the triangle around. As the numbers change, I still see that the ratio is always 2. So that tells us that in this case, this mid-segment AB is always half of the length of CD, which we call the third side. You can also see that as I move this around, that AB and CD, or no matter how I do this, they're always going to be parallel. I can prove this by calculating the slope. The thing that I don't like about this is it's going to give me a grid, but I can still see that the slopes right now are both 1.09. No matter how I move that around, they're always going to be, you can see the two slopes right there. As I move this around, they're always going to be the same. So I'm going to get rid of the grid there because it's kind of in our way. But you can see that the slopes are the same. So property number 1 is that mid-segments are half the length and parallel to the third side. So that's what we're looking at there. Okay, on to property number 2. Let me get rid of that stuff. Property number 2 is that the three mid-segments together create 4 congruent triangles. So as a proof of this, I'm going to make a triangle here. And then I'm going to actually copy that and show that if I move it there, that's the same as that triangle, it's the same as that triangle. So that one's definitely the same as those two, but how about the one in the middle? How can I prove that? Well, if I take the midpoint here, construct a midpoint, and then I double click that as a point of rotation, and then I take this thing right here and I transform it and I rotate 180 degrees, you can see that it ends up in that space. So all I did was rotate it 180 degrees and it ended up in that middle triangular area. So property number 2 states that the mid-segments divide the triangle into 4 congruent triangles, and they're all similar to the larger triangle, the original triangle. And I will show you that here. And say one way we know that is if we can prove that, let me get another one of these. We know that triangles are similar if the angles are congruent, and you can see the top angle is congruent to the top, and that angle is congruent to that one, and that angle is congruent to that one. So we know the 3 angles of the smaller triangle are congruent to the 3 angles of the bigger triangle. Therefore, it's similar. The next thing we're going to look at is medians. So I'm going to make a triangle. Definition of a median is a segment that goes from a vertex to the opposite midpoint. So I need to construct a midpoint, connect the two, and voila, we have a median. I'm going to mark it, those two congruent, because that's how you would mark a median. Congruent. So there's one median. One thing that's special about a median, it divides the triangle into 2 equal areas. So the way for me to measure this is to construct the interior of this triangle. And then go back and construct the interior to this triangle. And then measure the area there, and then measure the area there. Okay, pretty interesting. No matter how I move it, these two areas are going to be the same. They're going to be equal. Now, why is that? Well, how do we find area of a triangle? Is area of the base times the height. Well, as you can see, point C would represent the tallest point of the triangle for both triangles, the blue one and the green one. And you can see that AB is the base of the blue one and BD is the base of the green one. And the bases are the same and the heights are the same. Therefore, naturally, the areas are going to be the same. So that's the first thing you need to know about medians. Oh, yikes. Undo that. Let's see. Now, what we're going to do is we're going to look at, I'm going to construct the other medians. Construct midpoints. Then, as you notice, or as you will notice, when I connect all the medians, they all intersect in the same place. That's called concurrent. And there's a point of concurrency. That point of concurrency is called the centroid. The interesting thing about a centroid is it's the center of gravity. So if I were going to balance this triangle, or any triangle, I would need to find the centroid. And if I spun it around that point, it would be perfectly balanced. So the centroid is the center of gravity. The other thing that's interesting about the centroid is it divides the median, every median, into a 2-to-1 ratio. So if I measure that distance, and then I measure the distance from E to that midpoint there, you can see now that's a rounding error. It looks like it's not quite half, but it is, in fact, because if I take the calculator and calculate the ratio, take that one divided by that one, you can see that that's a ratio of 2, which tells us that the longer part of each median is going to be twice as long as the shorter part of each median, with that point E right there in the middle. So here's one way that I could mark this. I know that this segment right here is twice as long as this one right there. That's true for all medians that hit at the centroid. And that's about it for centroid. The next thing we're going to look at is angle bisectors. So create a new triangle, and we're going to bisect the angles. One thing that's true about one angle bisector, it's the set of all the points that's equidistant to the two sides of the angle that I'm bisecting. So in other words, this point right here, if I measure the distance from there to that side, and I measure the distance from point A to this side, that you see, hopefully you see, that those two distances are always going to be the same. No matter where along the perpendicular bisector it is, you can see right there, it's a distance of 1 centimeter to the two sides. The farther out I go, the distance increases, of course, but it's still equidistant to the two sides. So that's the first thing we need to know about an angle bisector. It's the set of all the points equidistant to the two sides of the angle that it's bisecting. Alright, so I'm going to construct some other angle bisectors here. And I notice once again that there is a point of concurrency. There's a point where all the angle bisectors intersect. This point of concurrency is called the incenter. Okay, it's called the incenter because it's the center of the circle that touches all the sides of the triangle. I'll show you in just a second, but one thing we need to know about the incenter is that it's equidistant to the three sides, and that's why we can construct a circle. To construct this circle, I'm actually going to have to construct a perpendicular really quick. Construct a perpendicular so that I can create a circle right there and connect it. I'll go ahead and hide this because we don't really need it anymore. But now I see that I have a circle. The incenter is the center of the circle that is going to be tangent to all the sides because it's equidistant to all the sides. It also happens to be the largest circle that I can fit inside of a triangle. So there's that's called an inscribed circle. The next thing we're going to look at is perpendicular bisectors. Now I've already constructed all the midpoints. Now if I want to construct a perpendicular bisector, I'll just construct perpendicular line. Now one of the definitions of perpendicular bisector is it's the set of points equidistant to two given points. So this point is on this perpendicular bisector, which means it's equidistant. A to B is the same distance as from A to this one, which I think is going to be C. You can tell that no matter where I am on the perpendicular bisector, that they are equidistant to the points B and C. Okay, that's the first thing we need to know. The next thing, I'm going to construct the other ones. Construct perpendicular, construct perpendicular. And I see once again that they are concurrent. The name of this point of concurrency is called the circumcenter. Circumcenter. The circumcenter, one of the key things that we know about it is that now it's the set of points equidistant to all three vertices. And because it means it's the center of the circumscribed circle. In other words, it's the circle that goes around the triangle. Instead of inside the triangle where we had in center, this is the circumcenter. It goes around the outside, touches all the vertices. And so I've got my triangle, and I can see that no matter how I move my triangle, that the circle is in contact with all three vertices. And one of the things we notice about the circumcenter is that it can, in certain kinds of triangles, it can be on the outside of the triangle or the inside of the triangle, or it can be on the triangle. And we'll need to know that the differences of when it's obtuse triangle, it's on the outside. When it's an acute triangle, it's on the inside, and therefore when it's a right triangle, it's right on the midpoint of the hypotenuse. That's our circumcenter. That was stupid. Okay. The next thing we're going to talk about are the altitudes of a triangle. The definition of an altitude is it goes from a vertex and is perpendicular to the opposite side. So in this one, I've already got it constructed. I've got the three altitudes are in red. And one of the things that's interesting about the altitudes is that when I make it a right triangle, you can see that the altitudes are actually the two legs of the right triangle. And then when I make it obtuse, you can see that the altitudes actually go outside of the triangle. In a normal acute triangle, they're all going to be on the inside. Either way, all three of them intersect at a point that's called the orthocenter. Orthocenter is the center, or it's not really the center of a circle like some of the other ones are, but it's just the point where the three altitudes meet. And you can see that also the orthocenter can be the vertex if it's a right triangle, and if it goes out here, it disappeared on me, but the orthocenter would be that point right there where if you extended the altitudes out, you can see the dashed lines, that would be, the orthocenter would be outside of the triangle. And that happens again when it's an obtuse triangle. In this picture, I have all four things we just created all in one picture. The one on the right, the one I have highlighted, is the perpendicular bisector. The second one right here is the median because it goes to the midpoint. The next one is the angle bisector. And then this one right here is the altitude. And one of the things that I notice is the altitude and the perpendicular bisector are going to be parallel in this case. But you notice that they're not all, these three are not all the same length. The shortest one is going to be the altitude because the shortest distance between a point and a line is along the perpendicular, and it is. Now, one of the things that's interesting is they can all become the same one when it's isosceles or equilateral. But in a normal scalene triangle, they're going to be different lengths.